Hello, my name is Thijs Veugen from TNO. I'm going to talk to you about secure integer division with a private divisor. This is joint work with Mark Opspoel from CWI in the Netherlands. I first introduce the problem. I talk about integer division, motivation for private divisor. I stepwise explain our protocols, show the performance and some conclusion. So the setting we are talking about is MPC. You see a picture about MPC, 4 players, each having their own data. Together they want to compute some kind of function, but they don't want to reveal the data to each other, and they want to be sure that f is computed correctly. This can be done with MPC. The MPC usually computes with integers modulo some number, which is sometimes prime, and we use the notation of brackets to denote secret shared integers, although a setting with homomorphic encryption could also be possible. We assume a basic MPC framework with functionality like additions, multiplication, secure comparison, random bit generation, and from that we build efficient protocols for integer division with a private divisor. What is integer division? Also known as Euclidean division. So you have given an integer dividend x, and the integer divisor d, and you want to compute x divided by d rounded downwards. Let me look for a pointer. So this formula, there's a clear relation with the modular remainder. So x equals the x div d times d plus the modular remainder. So if you know the one, you compute the other one, which also means that if you want to find the div, you can compute the number w such that the remainder is between 0 and d, and then you know that you have the right div. One remark is that integer division is not the same as multiplication with a multiplicative inverse in a field, because you have to do here some rounding with integers and it will not yield the same value. So basically we have 3 variants if you want to do divisor in MPC. Common divisor is a public divisor, so you have some constant which everybody knows, which can be a power of 2, and you divide a secret shared integer. It's also known as truncation. Other commonly known as secret divisor, so both numerator and divisor are secret, and you need some kind of iterative solution with mathematical and numerical mathematics to approximate the division result. And in between is a private divisor. So the divisor is known to only one party, and it's not public knowledge. And the basic approach has always been to create a secret divisor, so make a secret sharing of it, and then perform a secret division. But as we will see, it's much more efficient to use a separate protocol for this. You can use a private divisor, for example, when securely computing with transaction networks. You see 3 banks, each with their own color. It's a transaction network, so each node is a client, and an edge is a transaction, and the banks are not allowed to share the transactions, but they want to find financial fraud within the joint graph. You could, for example, use a PageRank algorithm to compute PageRank values. This is a formula for that, and within, if you zoom in, for example, on the PageRank value of node 2, so assume you want to compute the secret shared next iterated value of the second node, and it's some public value with some public constant, but here is a private division. It's the secret shared value of the PageRank value of the first node divided by a constant which is only known by the blue party. It's the out degree of node 1. And here the same with node 7. So here there's an example of private division, but there are more examples for that. So how are we going to build our protocol? Well, it's easy to start with a public divisor protocol. So we have a secret shared X, a public D, and we want to compute the division result. The way to go is to generate a large random number, which none of the parties knows. And you also need to know the the remainder of this secret random number and the dividend, the diff. And you could do that, for example, by first generating Rm as a uniformly random number between 0 and d, then generate a large random number Rd and compute R as a result. Then you have a large random number. You can add it to your secret dividend X, reveal Z. Z will tell you nothing about X because it's additively blinded. But given the public C, you can easily compute Z mod D and Z div D. And if you think about it, the X div D is more or less equal to Z div D minus R div D. And sometimes you need to subtract an additional bit. And whether you need to abstract that depends on the outcome of this comparison. Details are in the paper why this works. So this is an example of a public division protocol. So let's say we want to make this a private divisor. So we have secret shared X. We have a D which is only known to one party, which we call P1, and you want to compute the divisor result. So the idea is to reveal the same Z as before to P1, who can compute the diff and the mod, and from that you can continue until you find your output similar as before. But there is a problem here, namely how are we going to generate this random number without knowing D? How do you generate a uniformly random number Rm within this set without revealing D? It seems hard to efficiently do that. What you could do is we assume an upper bound on the divisor D. So we know the maximum number of bits L of this divisor. If we know that, we can generate L secret bits and compute Rm from that. So generating this is easy, but it turns out to be there is another problem, namely, well, we blind X with R, reveal Z to P1, but P1 can compute the model result with division by D. And this, unfortunately, is no longer uniformly distributed. So this reveals some information about X. And that's because 2 to the power L is not exactly, at least not always, a multiple of D. So the lower numbers of Rm are a bit more likely than the higher numbers, which makes that this leaks something. So we need to solve that. The way we solve that is by increasing Rm. So not with an upper bound of 2 to the power L, but 2 to the power L plus sigma, where sigma is the statistical security parameter. In this way, we can assure that this is still more or less uniformly distributed, so we don't have leakage, but we run into an accuracy problem because Rm is so large that Rd will no longer be the diff result of R divided by D. So we thought of a solution for that too, namely we shift the secret value X with a factor 2 to the power L plus sigma, compute Z in this way, and we don't divide by D, but we divide by the shifted d. And this turns out to work really well, because now if you want to compute x div d, it's the same as the shifted x divided by the shifted d. And so this is more or less equal to z divided by the shifted d minus r divided by the shifted d with some comparison bit, which we can still compute. And this division with z can be computed by P1. And this number we can generate ourselves quite easily, as we will see in the next protocol. Remember, this is the value r prime, and r prime should be equal to r divided by the shifted d. That can be seen here. So this is the shifted x. These two together are our random value. And the r double prime is relatively small. H is a multiple of d. And within the multiple of d, r prime is the multiple of the shift factor, and r is again small. So if you think about it, then you see that r prime is our random secret number divided by the shifted d. That means that it's safe to reveal z to P1. We let P1 compute the y and the y prime as this. P1 creates secret shares for that, and then the outcome is the y minus our r prime with a possible extra bit, which is the result of this secure comparison. The details of why that secure comparison works is in the paper. So this is our passively secure solution. Next step is an actively secure solution. So we have the problem here that P1 not necessarily computes the right y and y prime. So P1 needs to compute y and y prime correctly. How can we make sure of that? Well, the idea is that P1 is going to compute z prime, which is z div d. And to make sure that z prime is actually equal to z div d, we let him compute z double prime, which should be z mod d. We can jointly check whether it's a number between 0 and d. And we can check whether z equals the diff times d plus the model result. If this check holds, then we know for sure that z prime equals c div d. For that, we want to avoid carryovers here, modulo our MPC modulo. So we also need to show that z prime is not too large. But if we combine those three steps, we can assure that P1 computes z prime correctly, and given that, we can compute within the MPC framework y prime from z prime and y from z prime. Why is that? Yeah, if you look at this expression, this is c prime, so y prime will be the first L plus sigma bits, and y will be the remaining L plus sigma bits. And that way we can also make an actively secure solution. And it's time to go to the performance and compare our results with other algorithms. So we implemented the stuff in MP speeds. MP speeds have many variants. We used the one with 3 parties and replicated secret sharing modulo a power of 2 in a Amazon cloud. And the secret division protocol for MCPs is based on Katerina and Saxena from 2010. Unfortunately, they use the same algorithm for the public division, which is not really efficient, but I know, yeah, that's convenient. So because that is not a realistic version, we made our own public divisor protocol, which is a public variant of our private divisor protocol to make a more fair comparison. These are the results of the passively secure model, where the dividend is twice the length of the divisor. So here you see the blue line is our private divisor protocol. The red line is the public divisor, which should be lower than the blue line, but because of the, well, say, not efficient choice of MP speeds, it's above the blue line. And the secret divisor, it's the most complex operation. It's this green line, which takes the most time, of course. And in the actively secure case, you have a similar picture. You have a blue line, which is our private divisor. Our version of the public divisor is indeed below the blue line. The red line, public divisor of MP speeds, is again above the blue line. And the green line is again the highest of all, highest complexity. To conclude, we showed that integer division with private divisor is a useful building block in MPC. Transforming to secret division unnecessarily increases the complexity. It's better to use one of our protocols, where we show that the complexity is similar to the complexity of truncation. And this complexity is linear in the bit length of the dividend and of the divisor. We gave both passively and actively secure protocols. We implemented in MP speeds, but you could implement it in any other MPC framework. We showed that it's universally composable, so it can be plugged in all problems that you would. So this ends this talk. I would thank you for your attention, and if you have any questions, you know where to find me.